So my name is Natalie Kurbatova. I'm working for AstraZeneca. My organization, my department is called Data Science and Artificial Intelligence. And my main research interests are in data modeling, data integration for knowledge graphs, prediction algorithms, and some relevant topics. And today I would like to show you how we are building and modeling data for biomedical knowledge graph using Grakn technology. So it's very important to mention that we built the graph, this biomedical knowledge graph, with a particular goal. And my team goal is to predict novel disease targets. When I'm saying targets, means genes and proteins. So we're building the graph to predict novel targets, and it's important to mention. When we are building any biomedical or drug discovery graphs, we are usually talking about two types of data sources we are using. Kim, Konrad, and Tomás mentioned these data sources already. So we are dividing them into two big groups, structured data sources and unstructured. So when we are talking about structured, it means that there are publicly available databases where some type of data are already collected, like Ensemble for genes, UniProt for proteins, Campbell, PubChem for chemical compounds, and so on. That's a structured data sources. It's not very easy to work with them because they use different ontologies, different IDs, and so on, but still they're structured. It's slightly easier than unstructured, let's put it like that. When we are talking about unstructured data sources, at least in my group, we are meaning NLP-based results, so natural language processing. And again, the panel mentioned it already. It's a difficult story because NLP results are absolutely needed, especially if you want to predict novel targets, but it's a very noisy data. And the selection of the algorithm is extremely important, or algorithms, a combination of NLP algorithms and then aggregation of the results. So we're still working, it's work in progress. That's why it's in this gray color. We are using Cybert and pattern recognition algorithms at the moment for particular diseases we are interested in. Well, I will try to explain to you how we're using Grakn logical reasoning to improve data integration, because I think it's a really cool thing that Grakn has on board. And also we are working to put on board or into our work this knowledge graph convolutional networks, KGCNs. James was talking about a couple of weeks ago in another Grakn orbit. And we are planning to use it. We are trying to use it for novel target prediction. It's again work in progress at the moment. So this is our data schema from Grakn when we are building our biomedical knowledge graph. Very important here to say that we have three main entities. And again, remember I've mentioned we have a goal. We are building this graph with the goal, with the aim to predict novel targets. And we call this three entities here golden triangle, because we have to make sure that gene, protein, compound, and disease are connected as good as possible. So we're extracting all possible reliable data sources where we can put the edges to connect this golden triangle. So we've made a decision, that's a data modeling decision, to put together gene protein. So it's not two separate entities, it's one. And again, it's because we are trying to predict novel targets. That's our aim. And when you're modeling the data like that, it helps. If you are separating gene and protein node, you are adding a bit of bias and a bit of noise, at least in our experience. So few statistical numbers from the graph. So we've loaded this gene protein nodes. It's coding genes, around 20,000 what we have now. We have 11,000 and a half nodes, roughly 14,000 compound nodes and relations. So we're adding more and more every day. So the last time I checked, it was 656,000, but very possible that now it's more than that. So now few words about how, again, we are modeling different entities of this golden triangle I've mentioned. I will explain to you how we are modeling. We'll give some examples, and then we'll try to summarize what we think is very important from this story, kind of the message I would like to deliver. So first of all, gene protein entity is the simplest one, to be honest, in our biomedical domain, because it's relatively good annotated, and you don't have too many ontologies to work with and too many data sources to integrate as well. So we have gene name and chromosome as attributes for gene protein entity, and we have an abstract attribute gene ID. And then the real IDs can be uniprot if we have a protein, for protein, sorry, ensemble and interest. That's a special IDs for genes from ensemble and interest databases. Tomás was talking about the relation, so you can see the relation here, and it's very, very important relation if, again, you want to predict novel targets. Interaction between proteins and genes. So it's protein-protein or gene-gene interaction. That's the way we are modeling it here. It's also regulatory interactions when one gene is regulating the other one. And it's also sometimes gene somehow interacts with itself, or protein rather interacts with itself. So all of this is modeled into this relation. And now a bit more complex story around compounds. Again, to make this data model, data schema, a bit more simple, we've put together small molecules and antibodies. So we are not separating them. We call it compound, and that's it. And now the question of how we are calling things, because for chemical compounds, there are two very big databases, PubChem and Campbell, that are publicly available and broadly used. So PubChem in US, Campbell is European Bioinformatics Institute archive. The story is like that. In any publication where chemical compound is mentioned, you will probably find PubChem or Campbell ID. But the intersection between two sets from PubChem and Campbell is huge. It's around 95%, though there are chemical compounds that are unique in Campbell or unique in PubChem. So what to do? And we need some preferred compound ID to reference and to integrate the data. So we decided we're using Campbell when ID exists. We are part of Europe, after all, not European Union, but Europe, repeating Tomás's joke. But otherwise, if Campbell ID doesn't exist, so this compound is not in the Campbell database, then we're using PubChem. So this is how we are modeling the compound entity. So we have molecule type, as I mentioned, small molecular antibody, compound name, some other information. And then we have this IDs. Again, compound ID in our case is the abstract attribute, and the rest, PubChem, Campbell, if they exist, both. Drug bank, it's another database that broadly used for drug chemicals. And then we have preferred compound ID. And in order to choose what we prefer, we are using rules, Grakn logical reasoning, Grakn rules. And in this case, the rules are very simple. So we have two simple rules. The first is saying If compound has ID, Campbell ID, sorry, then it's preferred. If compound, and the second rule is saying, if it's not the case, then pub-chem ID should be present, and this is our preferred compound ID. Simple, yes. Needed, also yes, if we want to integrate data easily and not to do some extra work before we are loading data into the database. Now, the story becomes even more complex. Disease entity, that's our favorite part. And we spend a lot of time with Grakn guys trying to model it properly. Thank you very much, James, for helping in this. So the problem is that for diseases, we have multiple ontologies that exists. What I've extracted into the text here, EF4, Mondo, DOIT, Orphanet, it's a tiny subset, believe me. So one disease, that's the same disease, but it have multiple IDs, ontological IDs, and on top of that, there are multiple disease hierarchies. Why that's the situation? Because different ontologies are used in different subdomains, let's put it like that. For example, MESH, medical doctors, Orphanet is a specific ontology for rare diseases. EF4 and Mondo are usually used in a medical research results. So, but the same big domain, but a lot of subdomains that are walking around diseases. It's solvable in a way problem because some of the ontologies have cross-references. So you can find that this is chronic kidney disease in EF4 is actually has this ID in MESH ontology. So we can find cross-references, and if not, we can do some curation in order to put all these IDs together. So it is possible. Why we need it? That's probably the question you're asking yourself now. Why not to use one? Well, we are trying to integrate different data sources and different publicly available data sources using different ontologies. So very famous open targets using EF4, but PubMed publications quite often has ANSIT ontology IDs. Our, again, quite famous UK biobank, where the clinical samples and genomics data are collected, they're using ICD-10. Our collaborators, so AstraZeneca is collaborating with many companies, are using also their own ontologies, like Benevolent, for some reason Mondo. It's not a bad ontology, but that's what they decided to use, and we have to respect it. And maybe I'm wrong, so Conrad, please correct me if I am, but I think MESH is the GSK preferred ontology. I might be wrong. So that's why we need multiple, and that's the way we are modeling. So as you can see, I have disease entity, and then I have a lot of different ontologies. All ontologies we met trying to integrate different data sources. They're here, cross-referencing the same disease instance. Then I have ontology entity, and I'm describing my ontology, URL, name, and version, because version sometimes is very important as well. And here I have finally disease hierarchy. That's the relation I have to describe the disease hierarchy. And it is this, what was called by Tomás, the triple hierarchy. I've forgotten the word, sorry. When you have, so disease and ontology are part of the hierarchy, because we want to describe the disease ontological hierarchy in particular ontology. So EF4, this is EF4 hierarchical structure. In other ontology, is this ontology hierarchical structure. And now I will try quickly explain to you some examples to make it maybe clearer what I'm trying to say and why we need all these complexities on board of our knowledge graph in Grakn. So our very typical query is, give me all children of particular disease, let's say again chronic kidney disease, node using EF4 ontology. So this is EF4 ontology. So I want to have all these children, all of them. So I'm giving the EF4, I'm giving into the query my disease name, and I want to have all the children. So graphical representation, this is my parental disease, and I want to have as an output expected results, result B, C, D, E, F, G nodes. So all these guys. Again, logical reasoning, my favorite part of Grakn, to improve data integration. We're using Transitivity Rule here, and I think it's a very elegant solution. So what we are saying is very simple. We have this disease hierarchy relation that relates to diseases, and we have ontology to represent this hierarchical structure. And we are saying in our single ontology transitivity rule that if you have parent B and it has child B, parent A, child B, and B has a child C, then A is also a parent of C. That's pretty much all what we are saying. But it's enough to represent the hierarchical structure and to be able to run a query when I'm just saying, give me all children of chronic kidney disease using EF4 ontology, and I'm getting the results. It's really nice. And if I want, I can remove my ontology at all and get all children of chronic kidney disease according to all ontologies that I've loaded disease ontologies into my graph. So the flexibility is amazing, and when I'm loading the data, I'm very happy about the results. And about this data integration and logical reasoning. So very quickly, one more practical example with the same disease entity problem. So again, typical situation we are having. We want to replicate someone's results. And we have one ontology EF4, and the publication was mentioning like diseases with EF4 IDs, EF4 ontology, and some numerical values. For example, for the disease E, right? That's the disease of my interest in this particular case. And we want to compare this with some mesh ID ontology where results were presented using mesh. And the problem is, if it is a direct mapping, mesh ID exists, EF4 ID exists, we cross-reference them, happy days, nothing to do more here. But in the case of E, disease of interest doesn't have mesh ontology ID, so mesh is not, so this disease is not present in mesh ontology. What I can do? Well, logical thing to do is you go up until you are meeting the disease that has mesh ID, and you are saying, well, inferred mesh ID of disease E is a mesh ID of disease H. That's what we would like to get back. Using one more transitivity rule for this particular case of mesh ID. And why mesh ID is a problem? Because mesh is a slightly shallower ontology than the EF4, for example, so that it's not that granular. But still there are a lot of cross-references between them, EF4 and mesh in this particular case. So we are having two rules. If disease has mesh ID, happy days. This is our preferred, inferred, or best mesh ID. But if not, then we would like to go back and put down the ID from the parental disease. That's all what we are saying here. It sounds, and the diagram looks simple. The rule looks a little bit more complex, but believe me, it works and it's really nice. And it solves this slightly unpleasant problem we are having. So to sum it all up, data integration. There are two conventional approaches. So two types of approaches we have. Data factory. So you are integrating all your data before loading into knowledge graph. You're integrating and then you're loading. Another approach is that data schema supports data integration, or technology supports data integration, leading to flexible data loading and reasoning. So that's the case I was describing to you. I showed this slides to my partner, who is a software developer, and he was 100% sure that, of course, the first one, of course, you have to integrate the data beforehand and then load. Why? Why you want to do it in the database? It's crazy. So the truth is that if you are working in a research group, if you don't know what type of data sources you want to integrate, you have to be flexible enough. You have to be able to try and remove this data that were not interested, or to do this, for example, to replicate someone's analysis quickly to make sure that your data in knowledge graph are supporting the hypothesis that was published. So flexibility in the research case are very important for us. And the possibility to solve some problems like with this mesh ID in the knowledge graph directly with this ease of logical reasoning is very, very important. So future work probably doesn't matter that much. NLP results I've mentioned already. We are looking at Grakn 2.0. And the main thing is this graph convolutional networks for novel target predictions. But I would like to spend a few minutes on this slide, the summary slide. So what I was trying to show you and to explain. Grakn approaches, in this particular case, I'm talking about data schema and logical reasoning, help to maintain the balance between data integration, flexibility, and data validity. So there are other graph databases, and we're using them as well in AstraZeneca, that have a very flexible data loading policies. Flexibility should be there, but data validity is very, very important as well. A couple of months ago, the young junior colleague joined our team, and using another database, another technology, she loaded some movie data playing around. Didn't notice that even. So that was the flexibility. And next morning, we were very surprised to see in our biomedical knowledge graph some films and actors and things like that. So because data schema wasn't there, and you can load everything with ease again. Data sources evaluation. So that's what we are doing on everyday basis, like what data we want to put into the knowledge graph, what and how to add it into the knowledge graph. And when it is supported by data schema, at least you can be sure that the data skeleton was there and it's robust and trustable. It's quite important. I believe that Grakn provides a trade-off, very good trade-off between formal schema design, logical reasoning, and prediction algorithms capabilities. So here, what I'm trying to say is that, well, there are a lot of thoughts around how we are building knowledge graph in biomedical or drug discovery domain. Sometimes people are trying to put everything into knowledge graph. So all experimental data, let's put it in and see what will happen. In my experience, the data should be modeled first. We have to make some decisions before we are putting data in. And formal schema, actually quite flexible as well in the Grakn case, because you can add things into schema later on. And logical reasoning help you to find this good trade-off, what you are adding into your database. We also noticed that most of the prediction algorithms really depend on the data you've put in. So it's a bit of like what you've loaded into the database. That's what you have to expect to get out. So be careful when you are building your knowledge graph. It should be reasonable, and the noise level should be as low as possible, probably. So, and finally, this key choice, early or late data integration. That's coming back to this data factory before you are loading the data, or within the data schema. So for us, as a research group, this late data integration is very important and needed. But I believe that in every particular case, people have to make this decision. I'm working in AstraZeneca. We have an IT department of absolutely lovely and reliable people, but the response time is not a couple of days, obviously. So if you have new data resource and new problem with data integration, it will not be solved in days or hours, meaning that we have to do it ourselves. And when there is a technology knowledge graph that supports it, it's much easier. That's it. So thank you very much.
Bravo, bravo, Natalie. Thank you so much. I'm just going to quickly, here we go, reclaim host. Hello, hello. Natalie, thank you so much. That was it's really impressive, the work that you're doing, and it's such a pleasure for us to sort of see the inner workings of your thought process and how you've been have been working with Grakn. So thank you for that. I want to just check the Q&A and on Twitter. But in the meantime, Natalie, I've got a quick question for you, and a couple people in the chat have sort of alluded around it. But how does this approach compare to other approaches you've tried in the past?
Sorry, do you mean the data integration? So when you have the well, for me, the Grakn approach with this rules and logical reasoning is very nice and supportive, because if you are integrating everything beforehand, you are not flexible when you have new data source. So for example, I've mentioned this ontologies. Yes, cross-referencing we are doing beforehand, because it's too much to have it in the rules. It's just, it can become too complicated to deal with. But this preferred IDs or mesh IDs, the very logical things that you can solve on board when you're loading data, you can solve it in Grakn, that really helps and makes data integration and modeling it makes it into elegant way. It's really nice. So in comparison with other, so it's not possible pretty much in other technologies we've tried.
Yeah. Thank you for those insights. Any parting words before we say goodbye for now?
No, I'm muting constantly. Sorry. Thank you very much for the opportunity to present our work. It was really nice, and I really enjoyed your panel. I will definitely take a look. I think COVID is joining us all very much. So let's continue our work. I hope some of our insights might be helpful as well. Thank you.
Absolutely. Yes, let's continue to solve bigger and bigger problems together. So Natalie, thank you so much.